Hello. Okay. 11 a.m. Hi, STAT3004, STAT7304, week 11. 11 a.m. week 11. Can you guys hear me?
I think it's 12.
All right. Let me guess. You have some questions about the project, or any other questions, or about the problem set. You saw the problem set, right? Most of you are probably still working on the project. This is a problem set, which is the best practice for. No, it's week 12. Thank you, Ashley. Week 12. All right, week 12, but it's still 11 a.m. Okay, other questions? So you've seen the problem set. You got the project, which due date moved a few days. The questions, or I move forward on the study material and almost finish it on the self-study then. All right. If no questions on the assessments.
Sorry, I did have one question about the
last one. I'll just put the problem set so you see it. So in this problem set, let me just explain. You don't need to do all of them for credit. You can do all of them. So this is kind of 100 out of 132 points, something like that. So 100, or no, 30, whatever. 32 times 390.
Yeah, that's what I was going to ask about. I counted there's 32 questions.
I make a mistake. So it's 32 questions, 3 points. It's 98. Sorry, there was a mistake here. Let me correct. This is going to be 4 points each, not 3 points each. So you've got 128 points. So it's 4 points each. Okay. So you don't need to do all the assignments. I'll fix that. Yeah.
What happens if you get over 100?
In this problem set, a lot of the problems refer to problems from the books. Some of them not. I suggest doing all of them as practice for the exam. So exam questions will be similar to these in nature. And they're the best practice for the exam. What happens if you get over 100? You're capped at 100%. Okay. All right. If there are no specific questions here, let's get to the content. And that's here. No. That's here. No. That's here. Notability. No, so Shia, no coding for final exam as no coding for the problem set. So that was always the plan. The problem set is more analytic questions. You might want to graph a thing or two, or you have sometimes to solve the stationary distribution of a 3x3 matrix, etc. So you can use your software packages as kind of help, but no coding for the exam. It's really, the problem set is an example of the exam. The exam is, of course, much shorter, even though you have 24 hours to do it.
Yeah, yeah.
Right. So if I look at the self-study guide, so I know actually what I want to do. So we were here, and I actually had to leave the lecture because I had problems. Now you guys taught me how to do this. So this is where I stopped last week, last Friday. Come on. Sorry, this will take now a second. I must get to this. So look at Theorem 412, and that's an example of a Markov chain parameterized by two numbers, or by three numbers really, by lambda, mu, and the integer, the positive integer s. Okay, all right, and yeah, so look at this theorem. So you've got lambda and mu and the positive integer s, and is this Markov chain? RIP, LOL, LOL. That's what I found. Yoni. Oh, don't think you can hear our mix. No, I can't. Now say something.
Can you hear me? Hello?
Now I do. Sorry. Was there a whole lot of discussion? Yeah, go for it.
Oh yeah, for question 2 on the assignment, I'm still not like 100% sure what exactly it's asking. So Jack clarified on Piazza, but that kind of like, I'm still a bit ambiguous, it feels like.
This one.
Yeah, so present the expression for this approximation. So what exactly is that referring to? Is that referring to the deterministic or the probabilistic?
Yeah, it's just that there's not a whole lot to do in this thing except for going to the exercises on that chapter, yeah, and getting the expression for the approximation.
So is that approximation that t dash?
Yeah.
Okay. So okay. All right.
If you want to be a good citizen, then see how it's derived. But there's not much to do here.
All right, okay.
Because Evan was making out in the tute on Friday that was like, there's a lot more to that question than what we thought.
Yeah. Okay.
Well, it's right there.
Sorry, not Evan, Jack. He was saying that. Yeah.
Well, I mean, you can do more, but you know, the minimal, and that would give you the full points, is just, as said, present an expression for this approximation, the approximation that's referred to in the book.
Wait, so that one is the one with the one of the ones on the denominator is a -1, but the other one isn't.
Yeah, you need to put it in the language of R notation.
Well, no, because when it's done as a hybrid equation in the actual text of the book on page 59, it has -1, -1 on the bottom, but then in the question, it only has one of the things has a -1 and the other one's just the term.
One sec, let's see what you're speaking about. Where's page 59, or you mean page 58, is it? Or
58, maybe.
No. Okay, that's okay. No, but this is not an approximation. This is an exact expression, okay? This here is an exact expression. But this is not a nice expression from an analytical perspective, because it's this thing which is nice times this thing which is nice. I'm ignoring these two cases because they're just the edge case, okay? So let's ignore these for a second. Okay, they're just for j = 1, all right? So let's speak, this is kind of the interesting case there, right? So the two yellow things are nice. This is nice. This is nice. But then you have this plus gamma. And gamma is just a solution of a recursive, of a recursion, right? So it's not, this is the exact expression. This is not the approximation. This here is the exact expression. This is exact. Okay, exact. It's expectation of Tj is a sum of these things, and you write the sum, and you do some manipulation with the summations, etc., and you get this thing. Okay, so that's the exact. The approximation is Yeah, sorry, this question we're discussing it too much. It's not your fault. It's probably just too confusing. Discussing it and not just today, elsewhere, like in different meetings. But the approximation is this. This is like an expression that's easier to work with. There's no plus gamma something something. Okay.
Yeah, so what I was just saying though, with what Jack told us to do using that integral approximation down the bottom, if you make it j minus 1 to n, then you get it, except I always get the I minus 1 on the bottom. So I seem to get the log from the exact expression, not the log from that one there.
Right, but I actually didn't ask you to do that. Just to the project asks you to show this expression, write it, and then use Monte Carlo to obtain the error estimates.
Okay, so you just want us to write it?
Yeah, pretty much.
Okay.
Yeah, sorry for the confusion. All right, more questions about the homework, the project, or the problem set, now that I can hear you guys?
I was just going to say the word present isn't very meaningful. Like you say, present the expression. Like, what does present mean?
Yeah, well, present is like, if you present, here if you and me have a child together and then it comes out of me and I present it to you. I mean, present is done. I mean, this is not the best question. I mean, I'm sorry, this A is bad question. Present is to write. Maybe you can make a YouTube video about it and send me the link. Let's move on for this question, okay? Sorry if my sense of humor is just making me laugh and nobody else, but let's move on. Okay?
Yeah,
I laughed with you.
Thanks. All right.
Yeah, I got one more question about question 5C.
Yeah.
For the Monte Carlo, the matrix is actually quite large. How did you want us to get the expectations?
Okay, so when you do Monte Carlo, you're talking about what, 5B, you don't need to do Monte Carlo.
For 5C.
5C, right. Okay, so when you do Monte Carlo, you don't always need to write out the matrix. Okay, so, and that's an important point to be learned from this assignment. So look here, and let's go to SWJ. We're in SWJ10. Okay, so here are two Doob-Gillespie Monte Carlo algorithms implemented for a continuous time Markov chain. Okay, we're in SWJ10 again. Here's an listings 10.6. This is one of them. This guy gets his input in actual matrix. Okay, this guy gets an actual matrix. Now, sometimes constructing this matrix is a real pain, even though you kind of know the transitions, right? So writing the Q as a matrix can be a real pain, especially if your state space is two-dimensional. But still, you know the transition rates from any state to state, right? Those are what sometimes been called the little Qs, okay, the entries, okay? So here's another Doob-Gillespie algorithm that you cannot do by specifying the matrix, because in this case, it's actually of an infinite state space, continuous time Markov chain. Okay, so we're now in example 10.7. So this is in one of the video recordings discussed a bit further, right? So you know now what an MM1Q is. It's just a birth-death process with constant birth rates lambda and constant death rates mu. Okay, so but the state space is infinite. So in no way are we going to take a matrix Q and put here lambda, 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 and do it forever and mu, down lambda, lambda. We can't even represent it in memory. Still, we've encoded it in this Doob-Gillespie algorithm. Okay, so what we do is we look at the state. Based on the state, we see what the sojourn time is, and we make the jump. Okay, so you can, for the SIR model, your state space is finite. Okay, this model state space finite, I agree it's big. I agree it's big, but you don't have to construct the matrix to do C. You can. I mean, a computer will eat it up, but.
Okay, so do you just create bins then if you're counting sojourn time? So you just create like a bin around like an error band around like t=5 and then get the counts?
Okay, so what the Doob-Gillespie algorithm does is let's again, I'll put you in the context of the MM1Q, just because we're You're kind of learning by analogy here. So in element 1Q here, you're going to simulate up to capital time t. Okay?
Okay.
All right.
Yeah.
And now this specific implementation, by the way, you know, is recording everything, but you've also had implementation above that doesn't record everything. Like this thing records, this push records like every little state. The reason it records it is because this specific example actually plots the thing. Okay. So, oops. So what you're going to do is you're going to, in this problem, you're going to, there's different ways of doing it. So there's, I guess what you meant by bins is since we want at time 5, 10, 20, and 50, the efficient way is to let your simulation run up to time 50, and indeed have a vector that records where it is in 5, 10, 20, and 50. So you have a list or a list if you're in Python or whatever, or a vector or an array that has these 4 points, and you record, I was here, I was here, I was here, I was here. So you got these 4 numbers. But you do this for many realizations. So you got another realization. Okay, and you got a third realization. Now, when I put here I'm putting, this is like our state over these 3 realizations, but of course your state here is an SIR model. Your state is 2-dimensional, at least, right? Although you don't have to remember all the state, you just need to have the number of infected. Sorry. Well, what happened here? Too complicated. Okay, well, did that help, Madhusa?
Yeah, that helped. Yeah. Okay.
Okay.
That's good. Yeah.
There's another visit hour, by the way, today at 2, right? 2 to 4. I'm sure I'll see some of you there, which is perfectly good. More questions for now?
Okay. Maybe just the last one. For 5A, did you want us to solve that using a matrix ODE, or did you want to do that recursively? Because I had a lot of trouble doing that recursively.
5A is kind of like the present question. So on the same YouTube video where you solve 2A, you can solve 5A. Okay. Right is a synonym of present in my book of synonyms. So you go here to these forward equations and you just write them. Okay, but you write them in our notation. So it's a question to get you warmed up.
I think I was talking about 5B then. The ODE one, where you had to solve the ODEs, the system of ODEs.
Yeah, so this is a system of ODEs, right? This is a Kolmogorov forward equations in the SIR model.
Yep.
And you're speaking about 5B. Is it 5B?
So you want to numerically solve the forward equations?
Yes. Exactly.
So is that using the generator matrix and it's running it through?
Again, using a generator matrix might be harder, right? Because you need to actually populate this matrix, but you can in one of several ways. This is a bit more open-ended. So, you know, use your best ability to take this system of equations. Nope, not this one. This one, okay? Slightly different because we have slightly different notation, etc. And to find the solution at time t, the approximate solution. It's a numerical solution, right? One way would be, you know, write out the matrix and do a matrix exponential. But that, I agree with you that the state space is big. So you know, you're speaking here about n equals 100. So your state space is around the order of 10,000 states, right? So that's about 1 million, and matrix with 1 million entries. Right? It's like a matrix of 10,000 by 10,000. So you don't have to write out this is computationally challenging. This one is a challenging. I mean, it's not like just immediate. Okay, and you're getting your numerical solution would give you the probabilities. I'll go back here. I'll give you the probabilities. The most important ones are these. There, the probabilities that the system is in state I and j at time t. And from that, you only want to count the j's. So marginalize these out and then do an expectation. But I agree this problem's harder, or just requires a bit more delicacy, delicate action. Is that okay?
Yeah, okay, I was just wondering. Yeah, it's fine.
No worries. Okay. More questions about this stuff? Okay, so No, all good. So, and comment to for those needed. So we were here, and at which point I realized I don't have my mic. Thanks, you fix that. And then we got some questions. So this was just an example of what is this a continuous time or a discrete time Markov chain? That's like silly, simple question. It's continuous time. I mean, it's so silly you don't even want to answer. Is this Markov chain irreducible? The MMSQ? So lambda is greater than mu, lambda is greater than 0, is positive, mu is positive, so it's irreducible. Okay, so the Markov chain we're speaking about is a Markov chain that goes the birth-death chain at birth at rate lambda, 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 death at rate mu, death at rate 2 mu, death at rate 3 mu, up to state S here. This is state S, this is state 0, this is state mu S, okay, etc. Lambda, lambda. But here in state S plus 1, this is an S this guy, okay, death is straight mu S. So, because that means there are S plus 1 people in the system, S servers, S of them are being served, so death at rate mu S, death at rate mu S. It's like from this point onwards, it's kind of like an MM1Q in a sense, from this point onward to the right. Okay, so it's an infinite state space continuous time Markov chain, and if lambda and mu are greater than 0, then you can get from any state to any state, so it's irreducible. There's a single communicating class. Okay, but the point is that it can be one of those three things, and this is pretty much where we stopped when I had to go and handle my kids, and that's positive recurrent, null recurrent, and transient. Okay, so if lambda is greater than S mu, there's just not enough capacity in the system, and it goes to infinity with probability 1. Okay, so transient formally says that for any state in that class, which is a single class, there's probability that we never return to that state if we're there. Null recurrent is this very special critical case, which means, well, we return to each state with probability 1, but the return time is actually infinite, and that means there's no stationary distribution. So only in this case, this is like, let's call it the good case. This is where we're positive recurrent and there's a stationary distribution, and here it is. Okay, so that's it. Right. Now the next thing that in all this discuss, stop me for the question, please. So I was in this discussion, I'll stop in a second. So we spoke about discrete time, continuous time, finite state, infinite state, positive recurrent, null recurrent, transient, periodic, which is just a discrete time phenomena, or aperiodic, okay, irreducible or not, okay, all these adjectives from Markov chain. The last one, and I think that's the last one we're ever gonna speak about in terms of these adjectives for Markov chains, is explosive. And I won't say a whole lot about that, but I want us to see it, okay? So it's something that I believe is not even in the SP book. It's only in the MC book, in the Norris book. Let me show you what an explosion is. Here's an explosion. Kaboof. Okay, so we're in MC2. Okay. So what happens in an and this is not a general Markov chain, this is just, they start in MC with just a birth process, which is like a birth-death without a death. What's the simplest birth process? We even had a whole unit for it. What's the simplest birth process? Birth process? Poisson process. Okay, so Poisson process is a birth process with constant birth, right? So a Poisson process is like an MM1Q where nobody's served. Okay, that's like my airline company. I've been trying to get money back for a few months for a flight that was traveled. People just call them, but they don't serve us. bastards. Okay, so that's a burst process. All right, so now think if in a burst process, you might have a trajectory that starts at state like this, and then like this, and then like this, and then like this, and then like this. But what's happening here is that the birth rates are increasing in a crazy manner. Okay, so the birth rates are increasing in a way, so it's a process where you'd have, like, say, this is state 0, this is state 1, this is state 2, this is state 3, this is state 4, and imagine that you have here lambda, and here you have another, say, lambda. Here you have 2 lambda, and here you have 4 lambda. I'm just giving an example. Here you have 8 lambda, and here you have 16 lambda, and here you have 32 lambda. Here you have 64 lambda, etc. Okay, it doesn't need to be so extreme, but imagine that the rates were like this. Okay, that the rates were like this, such that when I'm in state 4, I have a very quick intensity that puts me in state 5. And when I'm in state 5, there's even a quicker intensity that puts me in state 6. And when I'm in state 6, there's a quicker intensity that puts me in state 7, etc. So trajectories will have the following type of nature. They're gonna have this type of thing, which is called an explosion. Okay, an explosion. Now, of course, if your state space is finite, who cares? Because you'll finish it for some finite state, and you might be stuck here for a while, but you know, I mean, let's say that if there's also death rates, you'll move down, etc. That's done. But if your state space is infinite, then there's a positive probability of explosion. And this theorem, which we don't need to dive into, it's one way of characterizing it just for birth processes, not for general continuous time Markov chains. Okay, so it says if you look at the birth rates, so these Q's, these are the Q's. Okay, so it says, and zeta here is the explosion time. Okay, so this means no explosion because the explosion time is infinity. Okay, and this means possible explosion or yes explosion. It's kind of interesting that in this case, you either always have an explosion or always don't have an explosion. It's not that there's potentially an explosion. This is something that in more rigorous probability we call a 0-1 law. Okay, so you'll have an explosion if this series is finite, and you won't have an explosion if this series is infinite. I mean, that's the conclusion for these specific birth processes. But more generally, this type of behavior is an explosion. Has anybody seen this in ODEs? Are there any people doing analysis and seen similar things in ODEs? I guess quiet on the line means nobody's seen this on ODEs. So I mean, what's an ODE? An ODE is, you know, you can have x dot or ddx equals a function of x, right? But imagine if this function of x would be getting so steep as your state grows, okay? And you can get such functions of x, and you can also have explosions in ODEs. So time doesn't run to infinity. Nice thing about Markov chain, the explosion time is actually a random variable. Okay, so this is a property that may exist in continuous time Markov chains with infinite state space. That's explosion. And that's that story. Questions? No. Okay, so that's it. And that pretty much covers all we were going to say about Markov chains. What I could do now is, for the rest of today, I mean, so my plan is we've got another 25 minutes or so I want to run through this reading of activity 9, which you should also do as you work on the problem set. I do realize it's the end of semester and you actually have a lot of things, so you might be only driven by things you need to hand in. Okay, so I'll still guide you on activity 9, and then in the next And afterwards, with the exception of answering problems in the problem set, we'll spend the time on probability and measure. So that's what we'll do in the remaining lectures. And I also owe you another lecture, which I'll put on video. Okay, so there'll be 4 videos on probability and measure. And you might ask me questions about the problem set or about your project in each lecture. So that's in the next week and a half. And then we're done. Part as friends. Okay. Questions? No? All right. So I'm going to go quickly through this reading. MC2, birth processes, MC2, section 2.5, section 2.6. Okay, so I just want to highlight what's on there. So birth processes, we were just here, right? And in this activity, you're actually going back and you're going to the MC book, which is more rigorous than the SP book, okay? And you don't need that full level of rigor for the course, but it kind of gives you a view of slightly more rigorous description of Markov chains. In the exam, you have access to both books anyway, okay? So this is a birth process, okay? We were just here, all right? Here's a generator matrix for it, right? And here comes some analysis that you could do on like in a simple birth process of the expectation, which is not always easy to compute, but the expectation of the state. I mean, you're lucky if you're able to compute the expectation of the state. In this case, you can. Okay, this birth process is a process like this, with Qi's as lambda I, and that's sometimes called the Yule process. Okay, and then we speak about explosion, which is clear. And a Markov property, the same type of Markov property which we had in discrete time Markov chains, just appears here for birth processes, so I wouldn't worry too much about that. And then there is a theorem that constructs birth processes via the jump chain. Okay, so I'm not going to discuss all of this, but the point about this book is they start with kind of birth process, and then they move in the next chapter to continuous time Markov chains. Okay, so it constructs the 3 ways to show a continuous time Markov chain. One is via the jump chain and holding time duration, and one is via infinitesimal probabilities, and one is via the Markov property. Okay, but we'll see a more general theorem like that for continuous time Markov chains in general. Okay, and then comes the introduction of the jump chain. What's a different name that I use for the jump chain? The embedded Markov chain. Okay, so it's a discrete time Markov chain with matrix, this capital pi, which is constructed as follows. Okay, so you go from this generator matrix to the jump chain. Okay, you see these are rates, that's the Q matrix, and these are probabilities. Of course, not all of the information of the continuous time Markov chain is in these probabilities. You also need to know the sojourn time in each state. Okay, then comes section 2.7, which focuses more on just explosion, and I've just highlighted the phenomena, but we're not going to speak about it more. Okay, so that's in the self-study guide. Skim. Okay, so skim that yourself if you're interested. And then section 2.8 introduces the forward and backward equations. Okay. So the first step is it's for a general continuous time Markov chain. Okay, so the first thing is to speak about the strong Markov property. And this is, again, you don't need to read this in depth, at least not for the content of this course. The point is that t is now a stopping time. So t is a random variable which depends on all of the history, but not on the future. There's a way to say that. It's measurable with respect to the filtration, increasing filtration of the process. This has to do with the measures theoretic description, which we didn't speak about yet. And if you know the value of t, that just means that when you shift the process forward, the process still stays Markov with an initial distribution with a delta I, meaning that it starts in state I with probability 1. Okay, it's a strong Markov property. And here comes the forward equation. Okay, so these are the forward equations. All right. And that's the theorem about the forward equation. Now, I remind you, just from a computational syntax perspective, these equations here, and that's very important for those of you guys doing the project now, which is most of you. These equations here, so P is a matrix, but the ijth entry of the matrix P here is not this ijth entry of this P. Okay, so the equations you have here, like what the authors of we're now in EM3. Okay, what the authors of the epidemiology book said, or the epidemics book, the equations here, the Pij is exactly as it's defined. Okay, it's assuming some initial state. Whereas your forward equations that you have here are, this matrix P is the matrix of probabilities of going from state I to state J in T time units. Okay. The matrix P of T is, of course, in itself a stochastic matrix. Okay. So there's a discrete time Markov chain defined by this matrix P of T. You could see this, for example, just in a very simple manner. Sorry, I'm jumping between the books, but that's kind of been the nature throughout the course. Okay, so here now we're in SWJ10. Okay, so here you've got, this thing is the probability of going from state I to state J in T time units. Okay, and that's what you, let me go different pen, that's what you'd call Pijt. Okay, that's the ijth entry of the matrix P. And that's nothing but the matrix exponential if you're speaking about finite state spaces. Okay, there are a bit more hardships with infinite state spaces. Okay, so that's the key thing I want you to take from this theorem. There are more technicalities which are not needed, not for most of the things we're doing. And then the next theorem speaks about the Q matrix. About the backward equations. So here it's P transpose T is Q times P of T. Okay. And I just need to mention this for those of you that will do further research in stochastic processes in next year's course, advanced stochastic processes or something like that. So matrices that form solutions of this, okay, matrices that form solutions of this are something called a matrix semigroup, okay? So if you have matrix functions, okay, P is a matrix function because it takes some time, S or T or S plus T, the matrix function satisfies this, it's called a matrix semigroup. Now sometimes people formally define continuous time Markov chains via matrix semigroups. We're not doing it here. We're starting with a model, which is the generated matrix. Okay, and that's a backward equation. Now, if your state space is finite, a solution to the forward equation is a solution to the backward equation. So again, forward was P of T, derivative was P of, let me write it. Sorry, I'll just do it here. So forward was P derivative of T was P of T Q, and backward was P derivative of T was Q P of T. Now, some of you might know, and in finite state space, the solution is just e to the power qt. P of T is e to the power qt. Okay, the matrix exponential. You will know, some of you will know that Q times e to the power qt equals e to the power qt times Q. So the matrices Q and e to the power qt, or in general, it's a property of matrix exponential, commute. Okay, so a matrix exponential commutes with the matrix inside the matrix exponential. You could just see this from the definition of matrix exponential. And that kind of hints at why both these equations hold. Okay. So the next theorem speaks about minimal right continuous processes, and we'll skip that discussion. So the whole discussion of minimal is when you specify your continuous time Markov chains through such matrix semigroups, then you have to speak about, hey, am I speaking about a minimal solution or non-minimal solution? But we're not going to touch that at all. So if you see this kind of minimal, it's not in the scope of our course here. Okay. And we're completely skipping 2.9, which is about non-minimal chains. But if any of you are interested in the kind of broader, more rigorous theory of continuous time Markov chains, then you'll need to see what non-minimal chains are. Next year when I do this, I might not do it within epidemics, and then it'll be more of just a book MC and less of the book SP. It'll be more of a mathematical course. Okay, so that was a skip on non-minimal chains. And now we're at no questions. Okay, I hope this is of some use. You could look at it and kind of look at the reading and know what you need to look at and what less. And now read MC3, section 3.1, basic properties. So let's go to MC3. Basic properties. So chapter 2, MC2, was kind of describing continuous time Markov chains, starting with Q matrices and speaking about pure birth processes and etc. And now you're kind of building Markov chains from the start. Okay, so this is actually worth a read. Okay, up to here, because it's just kind of a review of what a continuous time Markov chain is. Okay, again, I is a state space. It can be finite or countable. Okay, zeta, the explosion time, you don't need to worry about further, as long as you assume your chain is non-explosive, which will certainly be the case if it's finite. Okay, so that's what it is, and you've got your backward equations and your forward equations. Okay, backward equations and forward equations. Then you come to section 3.2, super quick section, because it borrows everything from the discrete time. So the class structure of a continuous time Markov chain, you just need to look at the embedded jump chain, okay, the discrete time jump chain, which forgets time, just remembers what state you were in, and they will have the same classes. Okay, and that's the story. Okay, so that was 3.2. All right, let's go back to the self-study guide, and then 3.3, skim hitting time and absorption probabilities. Okay, so hitting time and absorption probabilities play a role in your exercises, but the way it's in MC3 is for continuous time, and they're kind of analog continuous time theorems to what we've done in discrete time. Okay, so the main story is, again, there was a thing, if you remember, something we called first step analysis. We even did this in the days where we met each other in class. I was like in week 3 or something like that. We did it for the Gambler's Ruin, but now you're in a continuous time Markov chain. You could still ask about hitting probabilities, and hitting probabilities are boring for continuous time Markov chains because they just borrow from the discrete time Markov chain according to the jump chain, right? I mean, when you hit it exactly doesn't matter if you're speaking about hitting probabilities. These are hitting probabilities. Yeah, think of Gambler's Ruin. Are you going to hit Ruin, or are you going to hit, yes, I won with my gamble, for example? Okay, so that's what you're speaking about, hitting probabilities. But then if you get to hitting times, of course, you need to adjust the previous equations that we had for first step analysis and actually take the entries of your generator matrix Q into these equations. And that's the hitting times, okay? All right. So the whole lecture I've been seeing on the chat, RIP, LOL, can you hear us? Can somebody write something else just to know that you're actually there? Can you hear me? Hi, thank you, Ashfa. Yes, good words. Hi, and yes. All right. Okay. The next thing is section 3.4, where you're speaking about recurrence and transience, okay? Now here I actually spoke a lot, at least for your intuitive understanding of what recurrence and transience is, but these are now the theorems that underpin all of this, okay? So this is like, let's look at this theorem. so it says if a state is recurrent for the jump chain, then it is recurrent for the continuous time Markov chain. Okay, that's great. Because recurrence and transience for the jump chain is like recurrence and transience for the continuous time Markov chain. Okay, recurrence means you return to it infinitely often. If a state is transient from the jump chain, then it's intransient for the continuous time Markov chain. Great. Every state is either recurrent, meaning you return to it infinitely often, or not. Okay. And recurrence and transience are class properties, meaning that if two states are in the same class, then they're either both recurrent or both transient. Okay. Now, this theorem is an analog of something we briefly saw in discrete time, where to speak about recurrence and transience, you could speak about, you could integrate the probabilities. PII is a probability of xt equaling I given an x0 equals I. That's the ith entry of the matrix P of t, which solves the forward equations with the backward equations. So there was a similar theorem like this, depending on if the summation, when this was an n in discrete time, and now this is a theorem for continuous time. Okay, so that's recurrence and transience. And this thing is kind of important. So Zn is something you sometimes, just I want you to see the word, this is called a skeleton. Skeleton, yeah? So skeleton of my body, the bones inside the body, the whole things. The skeleton of the process x of t, which is continuous time, is a discrete time process that we sample every nh time units. Okay? And the skeleton and the actual processes share the same recurrence and transient properties. Okay, so that's Zn. Zn is not the embedded Markov chain. Zn is like the Markov chain if you'd sample it every h time units. Okay, that's not the embedded Markov chain. You don't sample it at every jump. Okay, keep it. All right. Moving on, we're going into section 3.5, invariant distributions. All right, so invariant distribution. Where in finite state spaces, an invariant distribution is a stationary distribution, but we're still not here about this lambda here, where you multiply, this is like a lambda, a vector of lambda, times a generator q, and you say it's a vector of zeros, okay? And these lambdas can be infinite. This is still not a distribution or not, because you didn't normalize sum of lambda I as well. Now, this theorem requires a bit of measure theory to read its statement, but let's see if we can do it. And we'll speak about measure theory starting hopefully Friday. So let Q be a Q matrix, okay? So again, a Q matrix is finite. Fine, infinite was also defined, okay? With an associated jump matrix pi. And let lambda be a measure, okay? Now, for the measures in this book, in general, a measure is kind of a generalization. A measure is a function over a set, okay? I mean, a probability measure is the most common measures used in probability, okay? Here, our sets are countable, so a measure is effectively a sequence of numbers, okay? So the two properties hold. Lambda can be invariant, meaning that lambda q equals 0. Okay, so this measure is maybe not normalized. Maybe you didn't put the equation sum of lambda I equals 1. And the alternative is you look at the jump chain. So you take a Nagian measure, okay? Mu pi equals mu that solves, this is like the discrete time stationary equations. Okay, but then mu I is going to be related to lambda I by qi. Now this theorem is kind of written in generality because you know, it's not speaking about just a stationary distribution, and it's not speaking about finite state space, and speaking about measure, etc. But let's use it a second just to go to the slightly simpler setting of that we've been dealing with, where, you know, unless otherwise needed, we assume finite state spaces. So say I give you a general matrix Q. Okay, and this is something I want you to think about, and who knows, that might be in the exam as well. Of course, you'll have time to think about it during the exam, 24 hours. Okay, if it is, or something like that. I'm just saying this is kind of something that one can do nice things with. So here is a generator matrix Q. Now, of course, I can write pi Q equals 0, sum pi I equals 1. Now, I can make from a generator matrix Q the, what they called here, I'll just use their notation, capital pi, which is the embedded chain. Okay, and it's a bit unfortunate this is capital I and here I use pi, but that's okay, that's lower pi. Okay, and then I can write the equations pi, let's write pi tilde, capital pi equals pi tilde, sum of pi tilde I equals 1. Okay, so on the left, you've got your equations for the stationary distribution of the continuous time chain. And here you've got the equations for the stationary distribution of the associated discrete time chain, the embedded chain. Okay. Now these two guys won't be the same. They won't be the same. Okay. They won't be the same because clearly here we've missed some information. Okay, just so you're convinced that these two guys are not the same, and this is what I kind of want to end you thinking about, is take the two-state chain. Okay, the continuous time will go like with rate lambda and rate mu, whereas a discrete time is, well, it's boring. It's so boring. It's actually, well, it's periodic, right? The discrete time one is going to go. The pi here is going to go with probability 1 here, probability 1 here, right? I mean, the matrix pi here is just going to be 0, 1, 1, 0. Okay. So, of course, this one, stationary distribution, doesn't have the same long-term meaning, or even though it exists. Okay, periodic discrete time Markov chains have a periodic distribution. So, the embedded chain, this pi tilde, is not going to be the same as this pi. Okay. However, there are relationships with them, and you see this relationship in this theorem 3.1, where you say if lambda is an invariant distribution for Q, and now if you take a distribution that solves the stationary equations for pi, this is this thing. I'm saying solves in these quotes. I'm putting quotes with my hands like solves because we didn't ask for some ui to be 1. Okay, but still mu I is just going to be lambda I with a proportion correction qi. And that really makes a lot of sense. Okay, these are not probability measures anymore if you do this proportion correction. Okay, but that's qi. Qi is the negative, is the sojourn time rate, is a negative of the diagonal of the generator matrix. That's what Qi is. Okay, so we'll continue still for, well, it still takes, I guess Friday we'll take a bit just more time on this before we get to the measure theory and just finish through this and through this reading. But also keep in mind this and just think about how to relate. I still didn't give you the full story, how to relate your discrete time stationary distribution of the embedded chain with a continuous time stationary distribution, which is different because this one speaks about proportion over times and this is just over steps. Hope that made a bit of sense. Are there any questions before we part? All I see in the chat is hi and yes. So there must.
For the exam, is that like how long should it take to finish the exam?
It should. So 70% of the exam would take under normal conditions, like 2 hours. In general, even if we didn't have World War C happening, for exams, I believe they need to be 3 hours anyway. And then 30% might take you kind of another hour or 2. But not, of course, you have all the time in the world, so you can work on it more. Okay, so 70% should be rather straightforward. 30% will be kind of, let's call them differentiating questions.
Is it open book?
Open everything, not open internet. Open.
Not open internet.
not open communication.
But what I'm saying is, if I just go on the internet and search for something, is that okay? Or
I forgot what the official regulation is. I just won't answer.
yeah, okay. Well, let us know closer to it. So, just wondering, when are we going to get our marks back from Project 1?
Hopefully today. Hopefully today. I'm going to do now a prayer for 30 minutes, and it might be after this prayer they'll be delivered. Hopefully today. Really. I mean, it's been hopefully today for many days, but really. I know you need them to see how you're doing in the public too. I realize that.
Yeah. Now, that's one very powerful prayer.
No, it's not really a prayer. I'm an atheist. It's just going to be a prayer. I'm going to continue marking.
Okay, thanks.
Right. Any more?
So will there be a visit hour after this session?
Oh yeah. 2 p.m. 2 p.m.
Okay.
Mm-hmm. All right. Yes.
Yeah.
So will you ask there? Is it Xian?
Yep.
How about
Or
you?
can I ask it here?
You can ask here. So let's close with your question, and yeah, let's have your question. We close with that. So what would you like to ask?
They are very quick questions. So like the first one is for question 4A, like the RSI that you want us to get the lowest RSI value, but I think what we have is only can have something like up to like 3 or 4 decimal places. So I'm just wondering, like, how accurate do you want our result to be?
Yeah, I mean, you need to use common sense here. I mean, it's like I can't really specify it. You know, this is where it's like a project and not a problem, right?
Yeah.
So, I mean, what you need to do is you need to say, okay, let's say you're really advising to a population that has to, you don't need to write all this stuff, right? But I'm just saying, let's say you advise to a population with 10 patients where 5 of them start sick and you've got this rate of infection, right? What's going to be your, no, sorry, this is a recovery rate. This is a recovery rate. What's going to be the rate of infection such that this holds? So, you know, you get it within the dynamic range. Okay, just use your best judgment of what decimal places are. Of course, when you're doing Monte Carlo, you can of course repeat your Monte Carlo if you'd like 5 times or maybe 30 times, and then get an estimate for the error, right?
Yeah.
Because you, yeah. There's also another trick which I didn't speak about. It's more complicated than what you're asking. What you can do is, as you vary this, you can keep the same seed. Okay, so if you know what keeping the same seed, like an SRAND or other ways of keeping the same seed, you're actually going to reduce the variance a bit of the Monte Carlo estimator, but not critical. So just use your judgment there. Did that
Sorry,
help?
pardon. I didn't quite get it. So what I'm trying, so like I just found the RSI up to 3 decimal places and just stopped there. And I'm just wondering, like, is that enough, or I need to?
Look, I think it's enough, but of course, if you give RSI after 3 decimal places and then you do and you repeat your Monte Carlo estimate and it's going to be completely different, then it's silly to give it after 3 decimal places, right?
Yeah.
You know what I mean? I mean, this is Monte Carlo, so you can repeat your simulation, right? Your simulation setup, and you get a different RSI. So you want to, you know, if you did it, yeah, you use your judgment there.
So that's just fine, right? Like I can just stop there.
Yeah, I must say, in general, in both marking project 1 and here in project 2, I'm quite lenient. You know, it's like not. I realize you didn't get the marks for project 1 yet, but I'm not too picky, just so you know.
Okay, and maybe like another question about question 4E. Like, I didn't quite get like are you just expect that we to like talk about the, sorry, can you just explain the question? Like, what are you expected from that?
4D, was it?
It's 5E.
Oh, 5E.
Yeah.
Yeah, okay. I mean, this is just the answer to this question is just a paragraph, okay? First of all, right? Assume now that model 4, you also have b greater than 0. Right, now what's b greater than 0? B greater than 0 means that you lose immunity with a certain rate, okay? So that means that when you have this b, this non-zero b, it actually means that you're like an SIR, but the system kind of returns back to being susceptible.
Yeah.
Right? So
yeah.
that means that your continuous time Markov chain is actually going to have a single big class, and it's going to be irreducible. Okay, because it's a single class. Right? So, and it even has a finite state space, so you can actually calculate the stationary distribution. So in a sense, you can run over time here, and you can say, I have like an epidemic. You know, you could say here, I'm doing epidemic number of infected. I'm doing an epidemic number of infected. I'm doing an epidemic number of infected. But sometimes you kind of lose, so you continuously stay infected. The question is, if you do such a thing, is the stationary distribution going to have meaning in practice? Now, the key to answering, there's not a correct, right or wrong answer. All has to do with the parameters, but you kind of need to get a feel for the parameters. Hold on, pause. Ned says, does A also need to be 0 for this to happen? Yes, yes, that's correct. You also need 0, for A to be 0 for this one. That's actually a fix, Ned. Thank you. Yes. Yes, because otherwise everybody can be susceptible, not a single infection. Yep. Well done. That needs to go there. Thank you. Okay. Still, as you write your single paragraph solution to this thing, just think about what the meaning of the stationary distribution is. I mean, if such cycles are going to take a huge amount of time in comparison to the time span you're speaking about, then stationary distribution is irrelevant. Okay, you need your Markov chain to kind of return to things fast enough for the stationary distribution to be relevant.
Okay.
It's a good one.
And yeah, and for the last question, it's like, can I just say like, if the number of susceptible and infected between a range, then C becomes something. Can I just say like, if the number of infected is greater than like 20, and then the C will become 0.01, something like this. Can I just?
Yeah, for sure. That's a function, right? So what you're saying is CSI is yeah. I mean, what you're saying is a, how do I get rid of this thing? Go away. Okay, so what you're saying is, you're saying, you know, if I greater than 20, then 0.1, otherwise 1, for example. Yeah, that's for sure.
Okay.
That's for sure. You just want to have it so that you reduce what you had here, which here is many people are getting around 95, meaning everybody gets infected. You want to reduce that to less.
Okay, thank you.
All right. Okay, everybody. So thanks, Ned, for this correction. I'll be at 2 in the visit hour room. Have a good one. Bye-bye.
Thanks.
Thank you. Bye-bye.